In this mini lecture, I'd like to talk about how you can find the pH of a buffer solution. This is the pH before anything gets added to it. Alright, so the first approach we take is we have our compounds, and we do the reaction just as we normally would. We'll have an initial, or we'll have the equilibrium. So the initial concentrations here will be 0.100 divided by 2 and 0.105 divided by 2. Now let me explain where the divided by 2 business comes in. What we've got initially are 100.0 mils of 0.100 molar AH, and we're mixing it with 100.0 mils of 0.105 molar A-. When we mix them together, that doubles the volume of the solution. We're going to have the same number of moles of AH here as we have in here. If we have the same number of moles but double the solution, the volume of solution, that means the concentration is now going to be halved. And that's generally the way buffers are made, by mixing solutions of the weak acid and its conjugate base. Hence the 0.100 divided by 2 and the 0.105 divided by 2. So these are the initial concentrations here. It says equal volumes, so we know what we're doing with that. Now at equilibrium, here's what's going to happen. I want you to note here that the concentration of H plus is 0. It has no choice but to increase, and it's going to increase by an amount that I'm going to call delta. You can use anything you like here, disease, x, delta, whatever you want as your variable. But the point is that the concentration of H plus is going to go up. Now the H plus had to come from somewhere. Where did it come from? It came from here. And it was 0.100 divided by 2. Now this will be minus delta. And this one will be 0.105 divided by 2 plus delta. Now the reason for that is because let's say we had 3 of these. If we had 3 of these breaking up into 3 of each of these, then what's going to happen is that we're going to get 3 H pluses, and we're going to get 3 of these, but that's already in addition to what we already have of the A minus, which is 0.105 over 2. So it'd be 0.105 over 2 plus 3. And then we would lose 3 of these acetic acids as well. So that's why it's minus delta. So that's the way that the minus and plus deltas work here. Now the next thing we can do is calculate delta. Now keep in mind we've got a Ka value, we've been given that with the problem. Since these are weak acids, and we know they're weak acids because they're buffers, the definition of a buffer is that it's the solution of a weak acid and its conjugate base. It has to be a weak acid, which means I can make this assumption and I don't even need to test it. I can just make the assumption and just use it. Because if it wasn't a weak acid, it wouldn't be a buffer to begin with. So we can assume that 0.100 over 2 minus delta is going to just equal 0.100 over 2, and 0.105 over 2 minus delta is going to equal 0.105 divided by 2. So like I said, I don't have to do the testing of that assumption. The Ka value is going to be CH3 COO minus, concentration of H plus, over CH3 COOH. Now I can sub all my values in. The Ka I was given, that's 0.105 divided by 2. And that's times delta over 0.100 over 2. Now I can calculate delta, and I would do so by multiplying 1.80 times 10 to the negative 5 by 1.00 over 2 and dividing that total by 0.105 divided by 2. That'll give me delta, and delta comes out to be 1.71 times 10 to the negative 5. Now that happens to equal the concentration of H+. Now I know that from the table. You can see that. Concentration of H+ equals delta. So now I've calculated delta, that is the concentration of H+. Now I just need to find the pH, and the pH is going to equal the negative log of the hydrogen ion concentration. So the negative log of the hydrogen ion concentration. And that would be, that's going to come out to be 4.77. So to calculate that, what I'll do is I'll take the log of 1.71 times 10 to the negative 5 in my calculator and find the negative of that value. It's going to be 4.77. So that is the initial pH of the buffer solution.